for the other ones which are coming in. So today I have this privilege of inviting Dr. Rajeevan from the Earth Science Organization, Ministry of Earth Sciences, to speak on a very valuable topic, the changing monsoon and its manifold implications. So we all take the monsoon for granted, and yet we also have this cliche statement we all hear about, that India is in India, everything is a gamble with the monsoons, and monsoons dictate all our lives. Before I comment on the monsoons and what it will be doing, I think it's best that we let the expert, Dr. Rajeevan, who's a physicist, and therefore he will speak about what are monsoon patterns like, have they changed, are they shifting, and what are the implications of larger climate change on the monsoon patterns. How would they implicate on the economy of India, life in India, and how do we actually measure this change, and can we predict it very perfectly, are also issues which need to be addressed. Largely, I can say that the monsoons have been a rather stable part of our climate system, and we do get the average rainfalls for a particular time period in a very, very systematic way. So what are the shifts and how the continents and the oceans changed in their thermal patterns are issues which Dr. Rajeevan will be highlighting. With this, I'd like to invite you to give this talk on changing monsoon and its manifold implications.
Thank you very much for inviting me to deliver this talk. I'm very honored to be here to give this important talk on changing monsoon and the manifold implications. This is the outline of my presentation. Initially I will discuss about the basics of what is monsoon, why we should have monsoon here, and also a little bit on climate change, especially on the basics of climate change. And because the later part of my presentation, I will be talking about linking the climate change with the monsoon system. And then what we have from our observational data, what we have found out whether monsoon has been changing or not with the observational data. And what is our future projection from climate models about monsoon? The monsoon is going to change appreciably. So if so, what are the changes we can anticipate? And assuming that there are changes, then what would be the implications in our social, in our different sectors like agriculture, water resources, health, or disaster management? Monsoon is basically traditionally defined as a seasonal reversing of wind and precipitation, and also there could be changes in the coastal circulation itself. The whole coastal pattern itself will be changing it. And so basically we define monsoon. So monsoon is not observed everywhere in the globe. Monsoon is observed mainly in the tropics, and I will show a diagram figure showing that who are the monsoon region. And so there basically the basic definition is the reversal of winds and precipitation. So there should be a dry phase, also there should be a wet phase. So that's the region where we call monsoon region. And so basically it is something like that. When we get summer, September, March, May, June, July, that's the summer season, our land gets heated up. Whole Indian region or South Asian region gets heated up. We know the Indian Ocean is south of us, so that's the ocean, and we have a land over north of ocean, Indian Ocean. And so during summer, land gets heated up than ocean. Ocean is the water, basically water, so the heat capacity is very high. So it gets heated up very slowly compared to land. So land temperatures goes up very, very sharply. Okay, so during summer, what happens is over the land temperatures are very high when compared to ocean. So we have a temperature gradient here. Temperature is more and temperature is low here. So we have a temperature gradient like this. And higher temperature means low pressure, low surface pressure, so atmospheric pressure. And so here the pressure will be low and here pressure will be more. So in the atmosphere it's like water flow. Water flows from a high pressure area to low pressure area. Similarly, atmospheric flow also is basically from a high pressure area to low pressure area. So basically in the monsoon season, what will happen? The air from southern hemisphere will come here, and because Earth is rotating, it will also rotate. And that's what we call southwest monsoon. The winds will come as the southwest monsoon. That's what we call southwest monsoon. The winds are with southwesterly. Ideally, it would have been southerly wind come from south to north. Because everything is rotating, the winds also will get reflected. And so we have southwesterly flow. So winter, the whole thing gets reversed. So we will get low temperatures here, and high ocean will be warmer than land. And here we have a high pressure here and low pressure. So pressure gradient also gets reversed. So this is the definition of monsoon. I can go show an example how it is. This is I may not secure this. I may not secure this. Yeah. This is for our winter. During winter, this is the temperature. It is shown as degree Celsius. And this is the November-December period. You can see that over the land, temperatures are cooler than over the ocean. Oceans are warmer. And during May-June, you can see that whole land over India as well as Africa is very warm when compared to over the ocean. The ocean temperatures are cooler. So this is the basic driving force of monsoon. Land temperature, this land sea temperature contrast between during the winter and summer. That's the main forcing for monsoon. And we have different monsoon. We have an Asian monsoon, which is defined here. We have an West African monsoon. We have an Australian monsoon here. The Australian monsoon, they get it during their summer. I mean, our winter, they get Australian monsoon. And because of this temperature gradient and temperature reversal and the pressure gradient, monsoon flow also gets reversed. So according to the rainfall pattern also gets shifted. You can see during our winter season, maximum rainfall occurs here. This is the rainfall in millimeters per day. You can see that maximum rainfall is coming here over the southern Indian Ocean and also here. So basically, south of equator is the zone where you get more rainfall. And during summer and when monsoon sets in, we get more rain here. So you can see the big difference here. As winter, we don't have any rain, hardly any rain. But whereas during monsoon season, the whole scenario gets changed, and we get a lot of rain during this monsoon. So this is our Asian monsoon. And also things have changed here. Also, you can see that it is a dry place here, and now during summer they get a lot of rain. So this they call it the North American monsoon, which is basically discovered very recently. And here also you can see the South American monsoon also they have, but among the monsoon regions, or Asian monsoon region is probably the most prominent monsoon. And among the Asian monsoon, we have two different monsoon. We call one is the Indian monsoon, another is the East Asian monsoon. East Asian monsoon, that's basically Chinese monsoon. China. Okay. And so this is the definition of monsoon. Some old definition of Ramesh and Samanjivan, and he takes care only of the wind reversal. And this is the region where monsoon is seen. And it's the latest definition with summer minus winter precipitation rate exceeds 2.5 millimeters per day. So then this is the whole region. So you can define different regions where monsoon is there, where Indian monsoon is there, very prominent region where we get a lot of rain. And so basically North American, South American monsoon, South African monsoons are not very prominent in terms of its complexity or importance to the rainfall. So in India we have two monsoons. One is southwest monsoon, June to September. That's the main rainy season for the country. It accounts for about 70 to 90% annual rainfall. And we also have a northeast monsoon, which is not well known when compared to southwest monsoon, but also less tropic northeast monsoon. But the northeast monsoon is basically important for South India, especially states like Tamil Nadu, Andhra Pradesh, where they get more rain during northeast monsoon than southwest monsoon. And that is restricted over southern, especially southeastern parts of India. And this is the monsoon rainfall, mean monsoon rainfall. This is the figure is prepared using about 6,000 NG stations of India. And you can see that this is the rainfall during monsoon season, annual rainfall, this is during monsoon season. So it looks like the pattern is same, which says that monsoon is the primary season, June to September is the monsoon season, which you get maximum annual rainfall. And you can see that during monsoon season here, the southeastern parts of India gets less rainfall when compared to annual rainfall. Okay. And maximum rainfall is over west coast as well as over northeast India, and decreases westwards if we go. And I'll talk about now, slightly shift my discussion to climate change. As we know that this is a beautiful diagram taken from almost 2,000 years of observation. And observation means we have instrumental observation only on last 150 years or so. But before that, we had observations from tree rings and ice cores. So these measurements were extended up to 2,000 years. And these are all the concentration of carbon dioxide, methane, and nitrous oxide. You can see that for many years, almost 1,800 years or so, the concentration remained almost same. There was not much change. And you can see that the sharp rise in the concentration during the last 150 years or so. So this is mainly because of the human activity. And so these are all basically we call greenhouse gases, which basically warms up the atmosphere, warms up the earth as a system, and carbon dioxide, methane, nitrous oxide. And we also have a problem with the halocarbon, and they are well known for their linkage to the ozone hole. These gases are supposed to affect the ozone hole. And if you really see the last 150 years of data, you can see that basic observational of carbon dioxide started somewhere in the 1950s in a laboratory observatory called Mauna Loa, it's in Hawaii, and very high quality observation. And you can see that this is the way carbon dioxide increases in the atmosphere. And you can see that there are some variations like this up and down. That's basically seasonal variation because of the vegetation changes. The vegetation is because of the summer, winter, because of that. So vegetation also gets changes, and carbon dioxide concentration linked to the vegetation. So these small changes are because of the vegetation. But over the many years also, you can see that there is a large increase in the carbon dioxide. Now the latest position is almost plus 400 ppm in the atmosphere. And this is decrease of ozone concentration at the two different places only. Northern hemisphere and the southern hemisphere pole. This is the Arctic and this is the Antarctic. And you can see the sharp decrease in the ozone, and this is the phenomena we call as the ozone hole in the Antarctic. And that is also is caused mainly because of the halocarbon, and that is also due to human activity. You must have heard about Monsoon protocol, in which many countries got together and they tried to reduce the halocarbon so that the ozone recovery will happen. And but frankly speaking, if you see these observations, that did not really happen. So Monsoon protocol did not really give the importance of the recovery of ozone hole. There are issues other than this halocarbon. Okay. And this is atmospheric aerosols. Aerosols are very small, minute particles which you cannot see from naked eye. But you can see when the smoke comes, you can literally see smoke plus aerosols, these are smoke. And especially winter, which is well known in Delhi, and that's mainly because of the aerosols. The aerosols also can affect our climate system and also can have a linkage with monsoon performance, monsoon circulation and rainfall. And this is the figure shows the black carbon concentrations. You can see that over India's large concentration. And this is sulfur dioxide emission. So that is during sulfur dioxide emission, from sulfur dioxide emission we get sulfate aerosols. And the sulfur dioxide emission, you can see the maximum seen over the eastern parts of America, Europe, India and China. These are the main industrial areas. This sulfur dioxide emission is basically from fossil fuel, burning of the fuel. And that is mainly concentrated in the eastern parts of US, Europe, China and India. And so I'll talk briefly about what is greenhouse effect, because that is very important when we talk about climate change. We know the solar radiation is the primary source of energy for us, the whole earth system and climate system. So it passes through the atmosphere, and half of the solar radiation comes to the surface of the earth, and half will be reflected. Some few will be reflected, about 30% will be reflected to a space because of the clouds and aerosols, and 20% will be absorbed in the atmosphere. So 50% comes to the air. But earth also emits radiation back. Okay, and it's with its own temperature. So that some radiation will go out. Okay, and if the earth doesn't emit back to its space, we will be more on getting this energy, and the whole atmosphere will be get heated up. So that's to get a climate equilibrium, the earth has to emit up. Okay, But due to this greenhouse gases in the atmosphere, some radiation gets reflected back, absorbed and re-radiated back to surface, and that warms up again. Okay, so that is the main. So these gases will allow the solar radiation to come inside, but does not. It prevents the radiation going out from the Earth's atmosphere to the space, and it gets reflected back, and so the Earth's temperature goes up. That's the main cause for the temperature increase, or we call global warming. And this is the global warming what we observed from so far with the observational data. You can see that this is the last 150 years of observation, and these are all trends. The changes over the period. For last 150 years, how much temperature has changed over different places, and you can see more warming over. You can see the whole globe has warmed up. The warming is seen not only in a small part; the whole globe is warming up. And there are small portions here, North Atlantic, and some portions here it is getting cool. But otherwise, most of the whole globe is getting warmed up. And the warming is more, especially in the northern polar region, and also some regions down here. And warming is of the order of, for India, it's almost of the order of 1 degree. For the last 150 years, so yes, Indian temperature over India has increased by about 1 degree. Mean temperature, this is the mean temperature. And this is the way temperature change over the globe. And you can see that these are 3 different data sets. 3 different groups have accumulated temperature data from all over the globe. This data contains temperature observation taken over the land observatories. We call meteorological observatories, where we take measurements of temperature. It's about 50,000 or so observations from over the land, and over the ocean it's our ship observation. Whenever ship goes, they take observations of temperature, pressure, humidity. So it's a combined land and ocean temperature. Okay, and they put it in terms of anomalies. You take 61 to 90 normal, then they subtract it each year from the normal, how much is the temperature. The global average temperature is 14 degrees Celsius. 14. Okay, and so this is anything departed from the 14 is shown here. So what we can see here is almost 100 years or so, the temperatures remain same. There's not much variation. It remains almost 14 degrees or so. And recent years, you can see that there is a small sharp increase in the global temperature, and that's mainly from mid-70s, 1970s. The mid-70s onwards, there's a sharp rise in temperature. So this is the alarming part of the whole climate change issue. And when the temperatures have been increasing, that's why the whole IPCC, International Intergovernmental Panel on Climate Change, has come, and there's a lot of discussion on climate change. So people have become more aware about climate change, mainly because of the sharp rise in temperature. We all thought that this temperature rise will go up like this. It will go on increasing it. But if you see very sharply, we see this circle, and I have highlighted this circle because if you see last 10 to 12 years, temperatures not increasing as we expected from the current rate. You can see that it has become a flat. Yes, it is a big flat. Temperatures are higher than many other years, but it is still not increasing. So now people are really puzzled why these temperatures are not increasing, just become flat. So there are few suggestions. One could be due to solar cycle. We have 11-year solar cycle with solar radiation. The magnitude of the solar radiation gets changed every 11 years, and now we are in the low solar phase. So that could be one reason. Another reason is that ocean plays an important role in absorbing the heat. And so when the temperatures are warming up, they say that the ocean must have absorbed more heat, and it must have deposited to the deeper of the ocean. So, and some observation of the temperature over the deep ocean shows that there is a warming, especially last 12 years or so. So there is one possibility that the atmospheric temperatures are not really increasing. That means the whole heat gets deposited over the ocean, which is not very good. Someday that heat will come up again.
Yeah.
Someday it will come up. Okay. And not only temperatures, and many other parameters also showing the effect of climate change. And you can see this is northern hemisphere spring snow cover, and snow cover in last few years it is decreasing. And this is the ocean heat content, not only the ocean temperature, but the whole ocean heat content also has been increasing last many years in a sharp rise. And this is the Arctic sea ice. You can see that the sharp rise is decrease in the Arctic sea ice because of the warming and this melting of sea ice. And so if somebody asks you a question, what is the One good example can show that the effect of global warming, you can easily say the CI, suffix CI. That's the best example you can say the effect of global warming. And you can see the temperature, RTGS extent is decreasing like anything. And sea level also has been increasing. Last 150 years or so, the 15 centimeter rise in the sea level, and that is mainly because of temperature increase. When temperature increases, ocean volume will increase. So ocean sea level will also increase. And now I'll come back to monsoon variability. Initially I talked about the mean monsoon circulation, why we should have monsoons and different monsoon systems. Now I talk about monsoon variability, which is more influence, it has more impact on our economy, our agriculture, water resources, and so. And so monsoon varies in different time scales. It varies on diurnal time scale. From within one day till morning, there will be rain in the morning, there will not be rain in the afternoon. There are some over land, mainly we get rain during afternoon, but over the ocean, we get more rain over in the early morning. So there are diurnal variations also. And after diurnal variation, even within the monsoon season, also there is intra-seasonal variation. Within the season, there can be, so for example, Delhi, it doesn't rain all 122 days from June to September. It rains only on few days. Okay. And you take any station, even Bombay, it doesn't rain all 122 days. And so this is seasonal activity. And also from year to year also in monsoon range. So some year you will have good monsoon, some year you will have bad monsoon, some year you will have a drought, some year you will have flood. And multi-decadal time scale also, you have every 30 years you have epoch of good monsoon, then another 30 years you will have very poor monsoon. So that also which happens. And also even century time scale or even 1,000 years time scale also there are some variations which we talk about the climatology. So I will be mainly talking about these intra-annual and decadal issues. So mainly monsoon variability is mainly influenced by natural forces. So this is basically a natural phenomenon. In addition to that, human activities also could contribute. The only problem is we are not able to separate it out, the human impact from the natural variability. Nature also forces monsoon to vary, but also the human activity also contributes it. But it's very difficult to separate out, well, this is a part of, because of natural variability, this is a part because of human activity. But ultimately we have to separate it out to find out what is the impact of human activity. I spent some couple of minutes on this environment diagram. This is the monsoon rainfall pattern. What I showed here is this is the rainfall average over whole India. We have about 6,000 stations or so over rain gauge stations. So we have this rainfall data extending from almost 1875 to 2010, of course I showed. And what we have done, if you take all rainfall average over whole India, we get 89 centimeters of rain during June to September. Almost 1 meter of rain we get during monsoon season. That's the meaning. And some years you get less than 89 centimeters, some years you get more than 89 centimeters. So you can, each year you can represent in terms of rainfall in percentage department. For example, 1 year is 88, 88 minus 89 divided by 89 into 100. So that's the time series we have shown here. And what I have shown here is, so this is basically year to year variation of monsoon, the bar. I showed some bars with red color, and some bars with green and some bars with blue. And meteorologically we call this month black for a red color year as a drought year, in which the seasonal rainfall is the deposit is more than 10%, minus 10%. And these are all called drought years. You can see that there are many drought years here, there are many drought years here, there are many drought years here. And this we call it excess monsoon years, more than 10%. That's a good monsoon, really good monsoon. And remaining years we call normal monsoon years. And you can see that very interesting phenomena which is observed really. You can see this epoch from 1900 to 1930, we had more frequent droughts. You can see that there are so many red colors here in this box. And afterwards, for many years, we did not have more frequent droughts. And again, we had an epoch here in which we had a lot of droughts. So there is a kind of a multi-decadal variation of monsoon rainfall. And if you really plot the rainfall every 31 years and plot it for 31 years running mean, and that is shown as a black line here, and which clearly shows that there is an epoch in which rainfall is less, there is an epoch in which rainfall was more, and there is an epoch in which rainfall is low. Okay. And we all thought that these recent few years after this epoch, we all thought it will go up again, and we will go to this positive epoch, which did not happen. Okay, so we are a little worried because you can see that it tried to go up. You can see that here it is trying to go up, and many people, many scientists have informed, even the government officials saying that we are going into a positive epoch, so we have good monsoon in the future. But we had three drought, very major drought during last 10 years or so. So that's really causing that epoch to come down. So question is why that is happening. So that's a question which we ask. Okay, so what I have shown here is there is a year-to-year variation of monsoon rainfall, which also is very has a lot of impact on our economy and as well as agriculture. And in addition, but what you can see that there is no long-term trend. So monsoon has been, luckily, the monsoon is very stable. All India monsoon rainfall is very stable. Every year we get some rain, and within the almost 10, within plus or minus 10%. So that we are lucky to have a good monsoon and a stable monsoon. Some years it goes below 10%. And what we have seen is there is a strong multi-decadal variation. Okay, this is I am talking about all India monsoon rainfall. And I will briefly mention why the monsoon rainfall is important. This is a famous paper by Lojana Gargill and her son, another Gargill, 2003. And what they have shown is how the rainfall variation is related to agriculture production in the left hand side and your Indian GDP. And what he has shown is here, these are all years, different years. What they have shown is less than negative rainfall. Negative rainfall in particular year can have a large impact on agriculture production, the crop production in the country, and that can ultimately affect the GDP. And you can see that it is not a linear curve. It is basically a non-linear curve. The effect on negative rainfall is very large when compared to the positive rainfall. So when monsoon becomes bad, monsoon is a drought year, its impact on GDP is much higher than when monsoon is good. So that means we are not sure, we are not able to make use of good rainfall into a good economy. But when monsoon is really going bad, that will really affect the GDP. And even now, also, even the dependence of agriculture on Indian economy is much less when compared to last 50 years back. But still, Indian agriculture can affect the Indian economy, and that is through monsoon performance. So if we have a very poor monsoon, it can affect still agriculture production and can also have an impact on GDP. And now you can see that there are years in which even 2% effect was seen in the economy. And some, so I told the last this diagram, I will go back to this diagram and explain again. And if you see data from 1950 onwards, you can see that this was an epoch in which you have good monsoon and this epoch in which you have poor monsoon. So if you take last 50 years and make a trend analysis, you will get a decreasing rainfall because in initial years you get a lot of rain and that has decreased. So some people who want to propagate that aerosols, that we release a lot of aerosols in the atmosphere, especially black carbon aerosols, and especially Western scientists, and they blame India that we are burning a lot of biomass burning. We are doing it, and because of that, there is a lot of black carbon aerosols emitting, and because of that, monsoon is decreasing. Okay, and so they have recently a paper came in Nature. It's Monsoon et al. 2011, and they showed that this is decreasing rainfall, and they attribute that aerosol is the main cause for the decrease in rainfall. And what I am highlighting is that is not really true. I told that there is a multi-decadal variation in the monsoon rainfall, and if you take last 50 years and do the trend analysis, this green line, and if you remove the multi-decadal variation, the trend line becomes very small. Okay. So the recent 50 years of decrease of rainfall is basically a natural variability. It is not to be related to aerosol.
Depends on the life of the aerosol.
Yeah.
The aerosol is short time or long time.
Yeah.
The effect will be seen over.
That's true. The black carbons are very short time. The life period is about 1 week. And so what I showed here is the all India rainfall. If you take rainfall over the country as a whole, there is no decrease or increase in the rainfall. It is a stable monsoon we have. But if you go region wise and do the trend analysis, there is a decrease. There are some changes. For example, if you take 51 to 2011 in monsoon season, and if you take the last 111 years or so, there are regions in which here, this region, the rainfall has been decreasing. And where even Kerala is well known for decrease of rainfall last many years, and we don't know the reason for this. And there are some places where the rainfall is increasing, especially the coastal places and parts of Karnataka and Jammu Kashmir. So there are areas where the rainfall has been decreasing.
The whole literature,
Yeah.
The 31 years is considered 64 years. The rain variation takes in 6. That's why it's coming calendar. If you see the annual calendar, it's 64. Based on 64.
Yeah, actually it is 64 years period only. Yeah, actually, 31 years moving average I told, but the cycle is 60 years. Yeah. And so the question is, why is the rainfall has been decreasing here? That's the question which we ask. So if you take rainfall average over the whole country, there is no decreasing, there is no decreasing or increasing rainfall, because the increasing and decreasing rainfall gets cancelled. So we don't get all India rainfall in a trend, but region-wise there are trends. And that we attribute to the decrease in the low pressure systems here forming here. During monsoon season, many low pressure systems form over the weather system. It's a very important weather system. It brings a lot of rain over this region. And that if you take 51 to 1980, these are the tracks of the storm. And if you take last 20 years or so, you can see that frequency has reduced a lot. And so decrease of monsoon lows or depressions over this region could be one of the causes for the decrease of the rainfall over here. That's one guess. Another important issue in monsoon rainfall is the extreme rainfall, very heavy rainfall even. Like the rainfall in Bombay we had 26 July 2005. You can see that on 94 centimeter rainfall occurred was near Santa Cruz within 1 day. And that has caused huge damage. The question is whether it is occurred only over just of the incident of one incident over Bombay, or it occurred commonly over India. But it occurs everywhere. You can see that this is places where heavy rainfall more than 10 centimeters in a day, 24 hours. And you can see this is a place where you can expect more rain, heavy rain. And if you take 15 centimeters, this is the area where you can, West Coast as well as central India, it's the region where you can expect more heavy rainfall spell, 15 centimeters. These are frequency ones. And if you take last 100 years or so, and if you average over this box, you get a time series something like this. And you can see that, and rainfall, so the frequency of heavy rainfall events has increased in the last many years, recent years. The sharp, right, you can see the mean days are like this, and here the frequency has shifted a lot. So recent few years we have been experiencing more intense or heavy rainfall events over India. Uttarakhand we had recently, and we had Gujarat rainfall. So these are some examples in which we get more extreme rainfall. And also along with the rainfall, of course, temperatures also have been increasing over India. And this is a temperature increase from 01 to 2011. You can see that last many years the temperature has been very warmer. And the trend here is about 0.6 degrees, which is also very close to the global warming. If you take average of the whole globe, also if you get last 100 years 0.6 degrees increase, and India also if you take average you get 0.4 degrees. So this is a small basics of climate change. Now the question is, these are all observed data. This is from the past observed data. We found out these are the changes in the monsoon circulation of rainfall that is happening. The question is, what we can expect in the future. Okay, so what we can get in the future, we are not astrologers to see how much we can predict, but we can do it scientifically, very scientifically, using climate models. Okay, and the climate model projections, for climate models are basically mathematical models in which we use physics of oceans, atmosphere, biosphere, and cryosphere, and we model the changes in the climate system. And for which what we have to do is, we should assume how much increase in the greenhouse gases is going to happen in the future. That's the main important agenda. That without that information, we are not able to project how much is going to change the climate. So that is the main agenda. We have to first find out how much carbon dioxide will going to increase in future, and how much methane will going to increase in the future. And that depends on many social economical factors. It's not a very simple issue. So the so-called intergovernmental panel on climate change, they have a dedicated expert team. They got together and they design some kind of future emission scenarios, because scenarios. And 4 or 5 different scenarios they projected. And using that future projected scenario, you put it in the model, climate model, mathematical model, and run it for many years and see how the climate is going to change. So I will be next few minutes I will be presenting those results, how these climate models are projecting. Okay, and that is mainly by intergovernmental panel on climate change. There's the latest report was released in September 2013, and if you want to see the whole report, it is available in this website. And this is an example of how the future future projections of scenario of carbon dioxide, different emissions of carbon dioxide. Somewhere in 2010, the value is close to 400. And so it depends upon how we going to control the emission. If we don't want to control anything, it will go like this. It will go like this curve. And if you want to put some restrictions, then different restrictions are there, and these are given in different metrics, 6.0, 4.5, 2.6, and 8.5. And normally this 4.5 is assumed to be a moderate estimation scenario. And if you take 4.6, what you can see that it will increase, but somewhere around 2060, we will assume that carbon dioxide will remain flat. There is no more further increase in the emission. And till then, we will allow the emission to continue. So that's the thing. And carbon dioxide, the basic problem is it's a very long-lived gas. If you stop here, does not mean that tomorrow it will decrease. It has a life cycle about 60 to 70 years. So whatever we emitted 60 years also will be available somewhere in the system. It may be in the ocean, or it may be in the forest, somewhere it will be there. So it will come out after so many years. So it's not very, aerosols you can control it because lifetime is very small. It's over 1 week of time. You can control it, but greenhouse gases it's not so, it's a long lifetime. And then we use, we use climate models to simulate what will happen in the future. And people ask question, how good are these climate models? I can give I will tell you the models are improved for many years, last many years models have improved. And this kind of coupled ocean atmosphere models we have been developing for last 20 years, so it is going on. And if you see the first initial models, the models are not so good, they are not able to reproduce many climate systems, many parts of the climate system, but now the recent models are much improved, models are available. And I can give one good example is, this is a rainfall pattern from observation. Wherever land is, it's our rain gauges, wherever ocean is derived from satellite. So it's the ocean, it's atmosphere, ocean melted data set, and this is how the model is simulated. You can see the broad pictures of rainfall is simulated by the model. The model is capable of reproducing the observed pattern, rainfall pattern. But if you look at region-wise, if you look in very more detail, probably there could be some errors. But if you see the large scale pattern, the model is able to reproduce it. Another important point which I can say that climate models are good, and if you really do the past observations and compare it with model simulation, and the red is the model simulation and the black is the observation. You can see that the model is able to reproduce the increase in temperature, especially in the recent years. You can see that the increase in the temperature, which I showed around mid-70s, that was really reproduced well by the climate model. So what I am highlighting is the models are good for finding out the future projection. There are some problems which I will come out little later. So these are some projections which I taken from the latest IPCC report, and this is the average over South Asia, how the temperature will change during many from 2006 onwards to 2100, and as different emission scenarios. And you can see that around 4.5 scenario, we can expect a temperature increase by 2 degrees Celsius by 2100. Another 80 years, 80-90 years, we can expect an increase in 2 degrees Celsius. And if this is the rainfall over South Asia, the models are showing an increase, but the increase is not so high. You can see that it's only having 5 to 8% or so increase in monsoon rainfall. So the good news is that the models are showing that monsoon we will get more rainfall in future. Okay, but that's not a full. We should not be very happy because there are some side effects which I will show later. So this is a spatial pattern of the same simulation, and you can see that warming is getting predicted everywhere, and warming is of 2 degrees Celsius or so over the Indian land, and precipitation trends are about 10 to 20%. You the precipitation trends over here. So we can expect about 10 to 20% more rain in the future climate. And this is another paper which they have only calculated only over India, the paper by Chaturvedi and 2012. And there also the answer is almost same. Over India, if you take only Indian land point, the temperature warming is around 2 degrees also, 2.2 or so. And increase in rainfall is also again 8 to 10% increase we can expect. And this is also shown here, temperature increase. If you see that 4.5, temperature increase is about 2 degrees or so, whereas the rainfall is increasing. This is a different pattern of precipitation change, and so you can expect the temperature precipitation change about 8 to 10%. So models are showing with systematic results or projections about future climate, and this is another important information which the models can give. This is very interesting. The left-hand side shows the projected change in number of rainy days. As I told that rainfall doesn't occur all 120 days, it occurs in only few days. So when we in monsoon season we call a rainy day if the rain is 2.5 millimeter early. If it won't rain on particular day, if it rains 2.5 millimeter, we call a rainy day. So out of 120 days, we have 25 rainy days. Okay. So these 120 days, we get all the 120 days are not rainy days. So few days are rainy days. And if you see in the future projection of the climate change, what the models are showing that the number of rainy days is likely to decrease a lot. And it is likely to decrease even by 14 days. Okay. So the number of rain days are going to decrease. But the projected change in intensity of rainfall is going to increase. You can see that projected change. So what we can expect is the quantum of rainfall we are expecting about 5% change, but it is going to occur in a few days, much less days, number of days, rainy days. We cannot expect 50 days of rainfall, but instead we will get 40 days of rainfall. But the quantum of rainfall intensity, when it rains very heavily. So we are going to experience more heavy rainfall spells in the future. That's the message. Very, very clear message. All the models are showing a strong message. We are going to get more heavy, intense rainfall spells. And we also did recently we did an analysis. This is very interesting. I will show that only the bottom figure. These red lines are the shown from the observation, and these are remaining blue is basically from the climate model projection. It shows if you take maximum consecutive dry days, for example, one day it did not rain, so the next day also it says whether it rained or not. So the consecutive dry day means days, number of days within one rain spell and another rain spell. Okay, and that day, if you really plot it, it is an increasing. That means maximum consecutive dry days also is increasing with using observations, as well as the models also showing that that is going to increase. And that is going to that shows this is a spatial pattern, this is the average pattern, and you can say this is from observation, this is from the model. Especially these changes are observed over the central parts of India, and models are also showing that it's going to happen over the main monsoon core region, where the more agriculture is also important. So this is very clear message that number of consecutive dry days are going to increase. We get very less number of rainy days, but the intensity of rainfall is going to increase sharply. And this is another example. Another interesting result is many models are also citing that withdrawal of monsoon is going to be late. And especially this year, you could see that the withdrawal of monsoon was very late this year. And that doing future projections also showing that instead of maybe 1st September or 15th September or Northwest India, these models are showing that over central India. So that means withdrawal is going to change, means if assume that there is no change in onset, the duration of the monsoon period is going to increase. So more number of monsoon duration, but less number of rain spell, but very intense rainfall. This is the message. Okay, so what could be the implications? There could be implication on agriculture, water resources, disaster management, forest, health, and many more impacts. And what people do is, now this is climate model, IPCC model results are available. We know what is the future climate is going to take place, and with a lot of some uncertainty that I will come out later. And with this information, with the future climate projection, agriculture people will use their own agricultural models and find out what could be their impact on agriculture. Water resources, people will do the analysis of what will be the impact on rivers and whole water cycle. And disaster management people, especially on intense rainfall event, tropical cyclone. Forest people will do their forest models and try to understand what will be the impact on their forest. And health people will study on the immediate impact on health, especially on malaria and so. So I have few results. I am not an expert on the impact studies, but this is taken from different literature. I will just briefly explain. I may not be able to answer tricky questions from you. And this is a very famous paper by Perry et al. They use very sophisticated climate agriculture crop model, and using the climate change predictions, what they are showing is when carbon dioxide increases, that's the main cause for global warming. It has a positive effect on agriculture due to carbon dioxide fertilization. Okay, that has a positive effect. It is going to increase the agriculture crop. But because temperature is increasing, it has a bad effect. It has a negative effect. But if we combine together and 2050, you can expect this is the thing. This is 2020 and this is 2050. And A, B is without carbon dioxide fertilization. So if you assume that with the carbon dioxide fertilization and the benefits of carbon dioxide fertilization, the models are showing over India about 2.5 to 5% decrease in yield crop yield. Okay, so the immediate impact on agriculture is negative. This is the model projection, and there could be a lot of uncertainties. And if you don't consider the carbon dioxide, then the impact will be much higher. So carbon dioxide fertilization is significantly improves the agriculture crop production. And another important thing is, especially on rice yield, this is a good paper by Krishna Kumar. Agriculture, especially rice yield, it depends on rainfall as well as minimum temperature, the early morning temperature, very important. So what is shown is the temperatures are, this is the departures on the crop yield. What you can see that when rainfall is low and temperature is also high, the drop in crop yield will be much higher. Almost you can get 12% drop in the crop yield because of low rainfall as well as increase in minimum temperature. And models are suggesting that it's not going to be much increase in rainfall, but there could be large increase in the minimum temperature. And because of that, rice yield crop can be affected with severely. And this is a report by Agarwal, it's ICA report. Basically, it is referred by Ministry of Environment Forest. They got a report on NATCOM. And this is 2009 report. I have just taken from that. What they show is the increase in carbon dioxide to 550 ppm increases the yield size return because of the carbon dioxide fertilization. But increase in temperature may reduce the yield by another 3 to 7%. And by 2020, the productivity is going to decrease by 10 to 20%. And so increase in droughts and pests are likely to increase production variability. And because of sea also is going to warm up, and that can affect even the fishes and also the fish productions and so. And so I told you that Ministry of Environment Forest has brought out a report in a couple of years, 3 years back or so. And it's called a 4x4 assessment for 4 regions: Himalayan region, Western Ghats, coastal area, Northeast region. It's available in their website. If you want to see the detailed report, you can see. And the 4 key sectors: agriculture, water, natural ecosystems, and biodiversity and health. That's a topic which they covered. And briefly explain, this is the 4 regions they consider: Himalaya, West Coast, East Coast, and North India. And briefly I'll explain. The water resources, this is a famous paper by Gossain et al. 2006 in climate change for the current time. What they have shown is this is the change in the water cycle. Okay, the river of different river basins, and because of the feature of climate change. And what they are showing is some rivers it is a positive effect, and some rivers like Sabarmati is going to affect very seriously because of less rainfall is going to take place. And especially moderate extreme drought severity is projected in 2030 for the Himalayan region as compared to other regions. And this is for forest. What they say is an increase in net primary productivity by 23% or so over Western Ghats. So this is on forest. And for health is very important. Of course, they do not discuss so many other issues. Only malaria was malaria only was studied, and they say it is projected to spread in new areas in Jammu Kashmir and in the Himalayan region. And in the northeast region also, this is likely to increase for a longer period. In the Western Ghats, no change is observed. In the coastal region, they say that malaria is going to decrease. And this is a result from Bhattacharya et al. What they show is, this is a so what they show is this is a malaria incidence. You can see that sharp rise during monsoon season. So that's the period you get more malaria, and that is go well with the rainfall as well as temperature. So if we assume that we are going to get more rainfall as well as we are going to more temperatures in the future, we can expect basically qualitatively we can expect an increase in the malaria incidence if other things are not really assume that other things are remain constant. All these model projections, we don't assume that it's the Bible. It's not. There are a lot of uncertainties, and especially when you go to talk about regional changes, especially over India or Pakistan or Bangladesh, and there are projections saying that Maldives or Lakshadweep Islands will go in the sea, under the water. So this kind of projection really is not really very certain projection. If you talk about global temperature, average temperature is going to increase by 2 degrees or so, and rainfall is going to increase by 10%, there's a lot of certainty here. There are many projections which we have very less certainty. So there's a lot of uncertainty in that, and that could come mainly because the model is not perfect model. Okay, even though I told that models have improved over the last 20 years or so, and now the models are too good when compared to models in 1950s or 1980s or so. But now models are improved, but still there are problems in the models. So there could be a lot of inaccuracy. And there are many climate feedback processes occur in the atmosphere, which the models are not able to reproduce it correctly, especially on clouds. For example, people say that if you double the carbon dioxide, we know that it is going to increase the temperature. The same temperature increase can be nullified if we get more clouds. For example, 10% of global clouds can reflect back solar radiation back, and it can cool the atmosphere. Okay, so by warming up, doubling carbon dioxide, how much warming can take place, the same amount can be reduced if we assume that the clouds are going to increase. Okay, so the models have the serious problem in reproducing future climate, future cloud projections. How the clouds are going to happen. And so that's the cloud, it's called cloud climate feedback, and there's large uncertainty available now. And also because of sea ice and also ocean feedback also is a little complex. The models are not able to do it very well. And also I told that we assume some kind of a future emission scenario. There could be large uncertainty because that's all based on social and economical factors. It can change. So tomorrow Indian government decides that we will emit more carbon dioxide, that is going to change the emission scenario, and that is going to affect the climate change. So there could be a lot of changes. So I warn you all of you that regional climate projection, don't take it everything in the Bible. There could be errors, and so the policy decision, when government takes a policy decision, the uncertainty should be accounted. Without uncertainty, they should understand how much uncertainty is there in the regional climate projection before they take a policy decision. And summary, just two more slides. Indian monsoon rainfall average over the country is highly stable. So we have very stable monsoon system. We are lucky to have a stable monsoon system, and no significant trend, only multi-decadal variation we have seen. And however, there are regional precipitation changes and trends we have showed, and frequency of monsoon weather systems is decreasing, and intense rainfall events have been increasing. That's very important aspect. And in the future climate, what they're showing is, models are showing is, monsoon rainfall amount is likely to increase in future, and mainly due to increase in water vapor content in the atmosphere, and intense rainfall events are likely to increase in future, so the frequency of flash floods also is going to increase. And dry spells and maximum contributed dry spells are likely to increase. That means we have less number of wet spells, and monsoon withdrawal is likely to be 8, and thus duration of monsoon is likely to increase. These changes will impact agriculture, resources, forest health, and disaster management. I think that's the end of my talk. Thank you very much.